Okay, so we're going to go through some practice questions for basic complex vectors. And our first question is going to be calculate the inner product, the standard inner product of two complex vectors, v1 and v2, that are in Cn. Now v1 is going to be equal to 7 plus I minus 1 minus 2I. v2 is equal to minus 1 plus 10I minus 5 plus I. Okay, now we basically want this in notation. Okay, so if you remember how to do these questions, what you're going to do is, I like to do this, I like to make like a funnel kind of and manipulate it one more time before I calculate it. So I like to do it like this. And then I like to put a dot here. This might not be the best way to say it, but I like to put a dot here because then I remember that there's something special in this step. I need to make all these components in this second vector to be the conjugate instead. So I will take out the pluses, and if there was minus, we would change that to a plus. And now I simply want a dot product of them, if that kind of makes sense. That just means there's no further manipulation. We don't literally want a dot product. So we're going to want the vector 7 plus I times minus 1 minus 10I plus minus 1 minus 2I times minus 5 minus I. Now this is simply normal complex multiplications, and if you don't remember how to do this, you can just do this normally by distributing both, how you normally expand in algebra. So we can just do this quickly. Minus 7. I like to first take this and then take this because those are our real parts, since I squared is negative 1. Okay, so minus 7, and then I squared is going to be minus, and we're going to have a negative 10 multiplied by 1, so that's negative 10, so we're going to have plus 10. And then for a complex part, we're going to have minus I, and then minus 70I. And this will essentially just 3 minus 71I. Right. Minus I, minus 70I. Perfect. It's looking good. And the second side is 5 minus 2. Remember that this is going to come out to 2I squared, which is minus 2. And then it's going to be plus 10I and plus I. Now this is 5 minus 2 is 3 plus 11I. we're going to get 6 minus 60i, because we have to add them up. That is our answer. And remember, the inner product gives you an answer in Cn. Okay, let me find the next question that we're going to attempt. And this next question is just going to be simple, finding a unit vector in the direction of a given vector. Now, a given vector is going to be v, which is going to be equal to a complex vector, of course. That's our topic for today. And we essentially just want to find v hat, which is how we denote a unit vector. Now, you might remember that v hat is just equal to the vector v divided by the norm of v. Now, how do we find the norm of v? Now, the norm of v, you might also recall this, is just the square root of, since it's a complex vector, the square root of this. And remember, the norm is always, regardless of whether it's a complex vector or a real vector, it will always give you an answer that is in Rn. That's because a complex number times its conjugate, so say z is a complex number, then z times multiplied by z conjugate is a real number. Now, I don't think I need to explain that anymore. You can test that for yourself by setting z is a plus bi, and then you'll see that z times z conjugate is just a squared plus b squared, and these are real coefficients and thus a real number. And that's actually going to help us a bit to calculate this. Calculating the norm of a complex number is very simple. Easy way is just looking at these components over here. Since we're calculating the norm of this one complex vector, and remember it's multiplied by itself, so we can apply this component rules, z times z conjugate. You can expand this yourself, but I'm gonna do the simple way, so you can use it or not if you want. This is just -1 squared plus 5 squared plus 5 squared. This is just 51. So v norm is equal to 51. That's a pretty quick calculation. Oh, square root of 51. Don't forget the square root. And we're just going to do scalar multiplication for this of 1 over root 51 with our vector v, like the formula states. And that is going to just be -1 plus 5i over root 51, then 5 over root 51, and that is our vector. And that should be the answer that you should get if you do this question. Okay, now is kind of a different question. It's to find a vector orthogonal to a given vector. Our given vector v, excuse me for writing v every time, but it's simple to say v is the vector. So this is our question. We want to find a vector that is orthogonal to this vector. Now, remember that an orthogonal vector means its inner product is 0. And when you're in Cn, it's the standard inner product. When you're in Rn, it's the dot product. But we're working with Cn, so we have to use the standard inner product. So it's going to be a little bit difficult. Now there are two ways to do this. You can set one of these to equal 0. We don't want the 0 vector, by the way. We're not allowed to use the 0 vector. Otherwise it's too simple. We can set one component to be 0, and we can just solve this. So we can say 6 minus 4i times another z, where z is a complex number, equal to 4 minus 9i. And this 4 minus 9i over 6 minus 4i. You just have to do complex division. So how you do this, 4 minus 9i over 6 minus 4i, and multiply by its conjugate, so 6 plus 4i over 6 plus 4i, you're just multiplying 1, because that's allowed. And then, oh yeah, but the concept is useful again. This times this is what? Oh, it's just 36 plus 16. And the top goes to 24 plus 36 minus 54i, plus 16i, which 50, that's just 60, minus 54 plus 16 is minus 38i, if I'm not wrong, and 36 plus 16 is just 52. And that's going to be our answer. Now, we're not done yet, even after this calculation. We can still simplify it a bit more, so I think it's always a good rule to simplify it if we can. So 60 and 52 are both multiples of 2, the easiest. We can start with that, and that's just 30 over 26. Oh, there's still multiples, so it might have been even 4. So how do we get rid of this? Well, that's 15 over 13. Now 13 is a prime number, so we're not going to have any multiples left. So we're all simplified there. What about the complex part? We're going to have 38 is 19 over 26. And 19 is also a prime number, so there's no more simplification. Now, we know that this vector multiplied by 6 minus 4i is going to be equal to 4 minus 9i. So, remember the standard inner product. You have to use the conjugate on the second vector. Our answer is going to be this vector. We're going to have 1 here. Okay, we're going to let 4 minus 9i come out from there. 0 in our second element. Actually, I think it's easier if we just write minus 1 here. And I'll explain that in just a second. And here, we want to add 15 or 13 plus 19i over 26. Now, why did we do minus 1? Because, say, let's allow, I don't know, c equal to 4 minus 9i. Well, c, we're going to get c by multiplying 4 minus 9i by 1. But if we have c plus another c, which is going to result from this times 6 minus 4i, then we're going to get 2c. We don't want that. We want them to cancel out. So by adding minus 1, we're going to have minus c plus c, which will result in 0. Why did we change the sign here? Well, remember the small intricacy of this standard inner product. Don't forget. It's a bit complicated sometimes, but make sure you always remember to not forget about it.